We're going to take a look at some ideas of energy, but not right away. First of all, I just want us to consider a simple situation. Let me show you that to you. A situation where a ball is just launched straight up, and we're going to take a look at this from the ideas of kinematics like we have been, and we're going to notice how the values of energy do change form, but they remain the same in terms of a total amount. So let's go ahead and take a look at some of the formulas that we would generally use. If something is being launched up in the air, its position is going to be described by the function y equals y sub o plus b sub o and so forth. For our particular situation, we're starting at an initial position of 2. We have an initial speed of 40 meters per second. And so this would be a general description of the object's position. If we take the derivative of this, we would find a general expression for the velocity. Or, of course, you could plug that information into the v equals v sub o plus at equation. If we look at a snapshot later, 3 seconds after the ball has been launched, we can use these formulas to determine where the object is at those positions. So it started off at 2 meters above the ground, but now, after 3 seconds, it would be 77 meters above the ground. And it began with a speed of 40 meters per second, but it has slowed down to 10 meters per second. If we take this information now and put that into this kind of magical formula here, okay, this quantity 1/2 mv squared plus mgy, that particular quantity, it turns out that the total amount stays the same. So if I put in the initial information here, the 40 meters per second and the 2 meters as the initial position, I end up with a value of 4,100 for this quantity, this again, this magical quantity, 1/2 mv squared plus mgy. And if instead I put in the values where the object was at 3 seconds, I get the same amount, this 4,100. So this value, this 1/2 mv squared plus mgy, seems like it's important. Okay, and of course it is. It is the amount of mechanical energy that this ball possesses. So the part of it that's the 1/2 mv squared relates to the object's motion. It has no bearing whatsoever where the object is. It also doesn't matter which direction the object is moving. Could be moving up, down, left, right. The kinetic energy, K equals 1/2 mv squared, only depends on the amount of mass and the amount of speed. The unit that we use for energy is called a joule, and a joule is defined in terms of these standard units that you would put into this particular formula. You would be taking a mass in kilograms times meters per second all squared. And so kilogram meter squared per second squared is defined as a joule. If instead we're looking at the object's position, regardless of what the object is doing, whether it's moving or not, if it's going up, down, left, right, that doesn't matter. Just based on its vertical position, it has energy due to the gravitational pull. And that is called the gravitational potential energy. Symbol for that is U, although sometimes you'll see resources call potential energy PE. It can be done, but it's better to call it U. You see that more often. The units for this are that same joule. We can see it by plugging in sort of what we would normally, mass in kilograms, G in newtons per kilogram, and Y in meters. But then a newton, if you think about F equals ma, a newton is a kilogram times a meter per second squared. And so it's that same value of joules. All right, so this is a very important quantity. This combination of kinetic and potential energy is called the mechanical energy of the system. And what I just tried to show you here, just through just a real quick example, is what it means for that quantity to be conserved. It means that the value, this total value of 1/2 mv squared plus mgy, that total value never changes, even though the individual amounts certainly do as the ball moves up or down or whatever. Now, when you're dealing with this sort of an idea, how we're going to use it, we're going to look for situations where an object, a single object, changes position. And so this would be a good example of where we'd want to use energy. We don't want to use it when we have a lot of information about time or where the direction of the velocity is needed, like as an answer or something, because these sorts of quantities are not available when we look at energy. Energy really just has to do with how the object's vertical motion changes and how the object's speed changes. Not its velocity really, but its speed. But this would be a good example of a question where using energy conservation is a great strategy. We're not going to worry about solving this right now. Let's just kind of think about what would be the story of this particular picture. So this is a possibility. You know, maybe this girl Anna is at the top of the hill and she gives herself an initial push of 2 meters per second. The hill is 5 meters tall. That's, again, the vertical distance. And we may be asked, what is her speed when she gets to the bottom of the hill? And we could solve this question, and we'll do it in class. But I want us to just take a couple minutes to think about what energy is and how I want you to really be thinking about energy. So let's take a look at this picture and see what we can say about it and how the energy changes. One of the ways we can visualize the way energy transforms or changes the method of storage is to use a bar chart. And so sometimes you'll see me use this, or you may use it within your discussions, where Anna starts off with a small amount of kinetic energy. She's not moving all that fast, 2 meters per second, and she's at the top of the hill, so she has some potential energy. And then later on, so this is a second snapshot over here, so we've got a different kinetic and a different potential energy. Later on, her kinetic energy has increased because she's going faster. And where did that energy come from? Well, it came from the potential energy, which when she gets to the bottom of the hill, y is 0, and so she has no potential energy. So this is sort of how we want to think about energy, how as one type of energy increases, as one way of storing energy increases, it's got to come from somewhere. And so as the kinetic energy bar went up, the potential energy bar went down. Another way to visualize energy changes is to use pie charts. I'm pretty sure that this is probably presented in your first physics class. So at the top of the hill, we have two types of energy. The energy is being stored as kinetic energy, and it's also being stored as potential energy. But then by the time the girl gets to the bottom of the hill, none of the potential energy is left. It's all in the form of kinetic. But the way we're demonstrating conservation here is that the size of the pie doesn't change. The size of the individual pieces changes, but the overall size, the overall total energy of the system is not changing. In class, we're going to look at these graphs, and there'll be a follow-up video after our discussion. But you can also represent energy using a graph by just plotting out how the potential energy changes. And again, this is a type of thing that we'll be discussing a little bit in class, and then there'll be a follow-up video to that. Thanks for listening.